All right, and so we are back for more, and this should be, I think, the last lecture to cover chapter 18, and which should, in theory, be the end of the lecture material, at least for the first exam. Obviously, just a quick comment, these lectures aren't comprehensive, otherwise it would be, hours long a piece and reading through every bit in detail. The idea is to give you guys kind of the broad overview of the important points that come out of the chapter, right? I'm assuming that you guys are reading along, following along, practicing along also, so please make sure that you're keeping up with that also, right? There's some excellent resources out there, different websites and different YouTube channels, all this kind of stuff that's available for you. I'm trying to post something out there for you guys from different sources, just so you just don't, just for the point that you don't just get the information from me. There's another way of thinking about, another way of saying, another way of kind of processing this. So hopefully, if you have a different source or combining everything together, then maybe we can come up with something that kind of sticks for you really easily. So that's the hope there. As always, I just got Teams set up this morning, so you should be receiving a link from that if you haven't already. And so if you need to reach out with me on there, feel free to send me a message, and we can set up some kind of office hour meeting or something like that. So anyway, the point that I'm really saying is, if you need help, ask, right? And we can figure something out. Okay, so the big idea of chapter 18 was the two mechanisms. We have the electrophilic aromatic substitution, which is a way that we have of adding functional groups to an aromatic ring, nitros and amines and alkyl groups and carbonyls and sulfonates. What else have we learned? Halogens, right? And we have all these ways that we have now of functionalizing the aromatic ring. And then we took that idea and we expanded upon that and said, okay, now that we can add one group, what happens if we add two? And we talked about activators and deactivators, ortho, para, and meta directors, and all this kind of idea that comes in there. All right, so we're going to kind of lump all that stuff together, and there's a new mechanism or a new series of reactions, I should really say, that we can get to work with aromatic compounds, and that is nucleophilic aromatic substitution, right? So nucleophilic. All right, so a couple of quick comments here, right? We talked about electrophilic aromatic substitution, where we generate a good electrophile and it reacts with the ring. Obviously here, we have to bring in a good nucleophile. So what does it mean to be a good nucleophile? Well, if you're a nucleo, right, nucleus positive, phile to like, right? So if you want, or you're seeking after something that's positive, you're a nucleophile, right? So we have to bring in something that has a negative charge, okay? So we're gonna bring in things with a very strong negative charges, so localized negative charges. Okay, so for you guys that are home, like, hey, wait a minute, that sounds like this would be a strong base that you're bringing in. Well, you're absolutely right. Okay, a localized negative charge is what we look for when we decide what makes a strong base. And that is what we're going to basically have to use to get this reaction to work in the textbook. So here's my quick commentary. Chemistry that we do on paper always tends to work. When you go into the lab, of course, we can change things around with temperature and solvents and these other kind of things that we can play with in the lab there, right? Pressures and all this kind of stuff. And so in reality, nucleophilic aromatic substitution is a lot more useful and maybe a lot more, let's say, practical than we might give it credit for within the context of this course. Okay, so what I'm saying with this is this will probably be a very short lecture, at least in terms of what we need to chat about. I don't want to give the impression that just because this is shorter doesn't mean that it's any more or less important. Although what we're going to learn in here will really be limited in the sense of, right, now let's tie it back in, right, we have to put in these very strong bases, and usually we have to elevate the temperature. And that's where the problem comes in, right? So under these conditions, right, we have strong bases, and remember, acid-base chemistry is always going to be the quickest. So there are limitations with doing nucleophilic aromatic substitution that come from this idea of having acids and bases around, okay? But let's take a look at one of the simplest examples here, maybe. Or maybe not simplest, but one of the first examples. Okay, so pause, right? You guys should be able to generate this starting from a benzene ring, right? So I'm asking you, do you remember how to do halogenation of an aromatic ring? Okay, we need Br2 and we need some kind of transition metal halide, so FeBr3 or AlCl3 even could work, or any of that. Okay, great. So if I bring in a strong localized negative charge, okay, and I heat that up, nothing happens. Great. All right, so if I do this, heat it up, nothing's really going to happen. Fair enough. Okay, let's tweak this just a bit. Now if I do this, okay, now if I do this, I will end up, right, after an acid workup, okay, I will end up doing this. Okay, so pause here for just a second, couple of quick points. I didn't explicitly show it, but there has to be an acid workup, okay? If we're under strongly basic conditions, we have to come back and do an acid workup with that. So we'll bring that back in another example, okay? But anyway, so what's going on here? So we have sodium hydroxide, we have to heat this up. What is different? The difference being what? I added a nitro group here, okay? So stop. What does a nitro group do to the ring? Okay, well, going back to the previous lecture there, we know that to generate, or excuse me, to put a nitro group onto a ring, okay, we have to, or once we put a nitro group on the ring, it deactivates the ring. It draws electron density out. How do you know? Well, it's got a positive charge on the atom directly bound to the ring, and it's got pi bonds, and we can draw these resonance structures with that. Perfect, okay? So this is important. When we want to do nucleophilic aromatic substitution, it's a slow reaction unless we put strongly deactivating groups on the ring. Nitros are probably the quintessential example, okay? So you put some kind of nitro group on the ring, it's going to tend to speed this reaction up, okay? The other thing that affects the rate of the reaction is what halogen we use, okay? We'll talk about that in just a quick second here. But the point being, now that we have a withdrawing group, now that the ring feels more positive, if you want to think about it like that, then this reaction starts to work, which will tell us something about the intermediate, the mechanism for this, okay? So here's what happens. So let's take a look at the mechanism. So what I will do is bring in some hydroxide then, okay? So strong base, powerful nucleophile, positive feeling ring, good leaving group with the bromine there, although we have to be kind of careful here, right? Because when we talk about good leaving groups, we're thinking a little bit in the SN2 sense, and that's not quite how it works here. So we just have to be cautious of what I'm saying with that, okay? So that's going to attack that carbon. Let me do this here, right, just for argument's sake. Okay. I'm going to hit that carbon, okay, where the leaving group is attached to, and that means I have to pop that pi bond up into a lone pair. And that's the key part here, okay? So here's this. That blue, and I'm going to draw this out explicitly like that because we're going to make the point here in just a second. Notice that the bromine and the hydroxide or the incoming nucleophile are still attached to that same carbon, okay? This is not a particularly stable functional group here. And we'll talk a little bit more about that, why that is in the carbonyl chapters that we'll be getting to in the next kind of big chunk, okay? But having a carbon that has a very good leaving group bound to an oxygen like that, that's not going to hang around for too long. But look, Now we've got a negative charge, so a carbanion. Now we haven't run into that too often in terms of intermediates, right? We've talked about Grignards and organolithiums and that kind of stuff, right? And where we see or where we have negative charges kind of hidden or stabilized with the counter ions, right? The transition metals or the group 1A metals, right? But this is an intermediate, so it's similar in terms of what we need to do as compared to a carbocation, right? So we've got a charge we want to stabilize, so that's all I'm saying. So let's do a resonance structure, right? And I think you guys can probably see why we need a withdrawing group on the ring, or why a withdrawing group really speeds things up. Okay, double bond O, negative here, positive there, negative there, okay? So let me zoom in here for just a second on my fantastic drawing. Let me turn this into the best nitro ever, okay? Perfect, oh my goodness. Look at that bond angle. Okay, so now we've got a negative charge next to a positive charge. Good stuff. We can also draw an additional resonance structure, okay? So now we're gonna push that negative charge onto that oxygen there, okay? So let's do that. Hope I don't run out of space here, although I already know I will run out of space, because that's how it goes. Br blue and O, positive charge. That's going to be negative still. Now this is going to have double bond. Negative there, there, and okay. Got it, right? So we make a double bond here, which pushes a negative onto an oxygen. Good thing, right? Oxygen, pretty good at stabilizing negative charges, okay? Now we're just gonna cascade through the rest to get to our product, okay? So we're gonna cascade through the rest. I'll draw these in red just for argument's sake here to make things a little bit easier to follow. So that arrow, right? That arrow, that arrow, that arrow, okay? You with me? We pop this back down to a nitrogen oxygen double bond. We kick this pi bond over here. We move that pi bond there. These three arrows reform our aromatic ring while we kick off the best leaving group that we have, right? So this thing is a leaving group, but not until we go through a little bit of a shenanigans, right? It's not just like an SN2 reaction where the nucleophile comes in and the leaving group leaves immediately, right? We have to go through this kind of stuff that's here in the middle, right? So what's our product look like after this? Well, if we take everything and put color with it, right? So, see the nitro here, right? Got that, positive charge there in red, that in red. We'll have that, we will have that. And this was in green, okay. Fantastic, okay? So following the arrows, here's where we would get. Got to pause though, right? We are under basic conditions. This is a particularly acidic hydrogen, right? I think it's got like a pKa of like 10 or something like that. A pretty darn good acid, especially under these conditions. So technically this would be deprotonated, and then we would have to come back and reprotonate it with acid workup. But this is the mechanism for a nucleophilic aromatic substitution. Or what I should say, this is one of the mechanisms, okay? So now, why is this useful? Well, we know how to add withdrawing groups, okay? We can either do a Friedel-Crafts acylation and add a carbonyl group, although we have to be careful, okay? Nitro groups are far better. And we know how to do a halogenation, and now we've got a way of putting an OH there. And that's not something we really had before, right? Didn't really have a great way of adding an OH directly to the ring, but now we've got this here, okay? A couple of quick comments. Fluorine is actually a far better leaving group than bromine is, okay? So if you have a fluorinated aromatic ring, then that's going to undergo I almost kind of got ahead of myself here. That's going to undergo the nucleophilic aromatic substitution far better, Okay, that's going to undergo the nucleophilic aromatic substitution far faster, I should say, than bromine will. Really, if you want to do this, we want to stick to fluorine. Chlorine is okay-ish, right? But if we were in the lab, we would definitely want a fluorine instead of a bromine there to do this. The problem is adding a fluorine is not always so straightforward. In fact, we haven't learned a way yet to really add a fluorine to the aromatic ring, although there are some examples in the book and you're more than welcome to use them, right? So I'm not saying that they don't exist and it's impossible, it's just we haven't explicitly covered them just because it's very situational. But this will be one situation where you might want to do that, okay? Adding fluorine and then coming through and doing this. All right, so let's continue on this, and there's another mechanism that's at play. So if we don't want to use sodium hydroxide, or if we want to do this on an if we want to do this on a deactivated ring, sodium hydroxide works fine. If we want to use this on maybe, let's say, a neutral or even somewhat activated ring, we have to kind of change conditions, okay? So here's what I mean, all right? So kind of starting out with what we had there, right? We'll just go with a chlorine instead. If we do sodium hydroxide and really heat this up. So before, on the previous example, we maybe get it to about 100 degrees-ish or so, that's fine. If we wanted to do this, we would have to get it up to like 400 or something like that degrees, right? How many things survive, how many organic compounds survive at 400 degrees Celsius? The answer is not too many, okay? Your stuff will start to decompose. You'll get a lot of side products. Stuff, no one practically is going to do this reaction at 400 degrees Celsius unless there's some kind of industrial way of doing it. That's all I'm really trying to say. So we can come up with a different way of doing something, or we can come up with a different methodology. So no reaction except high temp, right? All right. But there were a set of chemists that came in and they used another very popular set of nucleophiles, which we have actually dealt with, nucleophiles and bases, I should say, where they took some sodium amide, NaNH2, and they put this into liquid ammonia. Okay. And then if we do this reaction, what we will end up with our product is we end up swapping the chlorine for an amine. Ooh, fantastic, right? So powerful base, a really good base. Far stronger base, well, yeah, I could say that. That should be a fair argument. Far stronger base than sodium hydroxide is, okay? Now, where have we seen sodium amide and ammonia used before? Well, remember, this is where we used this to form alkynes, right? We used this setup to form alkynes, so we know they are powerful bases that can even deprotonate vinyl carbons, right? So if you go back and take a look at your notes for that, we have vicinal and geminal dihalides, and if we put these under these conditions, then we would end up generating an alkyne. And here we're gonna essentially do the same thing, okay? So stop. If I just said a bunch of word salad to you, say what in the world is an alkyne or a geminal dihalide or vicinal, all that stuff, go back and take a look, okay? So how do we generate an alkyne? It's very similar conditions, and that's essentially what's gonna happen here. We're gonna make an alkyne, sort of, okay? But anyway, so we have a powerful base, just like before. To get our product, we're gonna have to come back and add some, do an acid workup at the end, right? Just to kind of clean things up is what it is, right? So here's the thing though, right? So this works fine. You might say, great, right? This is liquid ammonia. Liquid ammonia is around at negative 30 degrees Celsius, something like that is what it is, negative 30, negative 40, right? So this is actually fairly low temp and this works fine, right? There's a problem though, okay? So if I switch and do a derivative, right? So if I go to the methyl chloroderivative there, right? So that I end up getting these two products out of it. Okay? So here I could say stop, explain this to me. And the answer is you can't, right? You guys already have the tools and I already gave you the big hint about this. Can you guys propose a mechanism to get from here to generate these two products, okay? And the answer is, we're gonna have to go through an alkyne intermediate, right? We're gonna have to go through an alkyne intermediate. So let's take a look at what's going on here, right? So let's take this guy here. I'll put this here, just I think it'll be a little bit easier. I'm having trouble drawing this morning. I don't know what's going on. Okay. Let's bring in our sodium amide, right? So there's nitrogen, 2 H's, big negative charge on there, right? Powerful base. It's going to act like a base. Okay. What's our product here, right? Or what's the intermediate, I should say. Well, let's take a look. Okay. Got this, we got this, we got this. Chlorine's gone. Let's put on a blue bond there, and then we ended up forming that. Ooh. Do you guys see the problem here? This is an alkyne, and we would call this a benzyne. And we know this has to exist to some degree because we've done tests on this and all this kind of stuff, right? And they talk about that stuff in the book, and that's great. But what's the problem? Well, the problem is, right, what is the hybridization or the geometry of an alkyne? Well, it wants to be sp hybridized, which means linear bond angles, 180 degrees. But it's trapped in an aromatic ring. Oof, right? So it's, 60 degrees in there. Excuse me, not 60 degrees, 120 degrees in there, right? So there's a lot of strain on this, and that causes some, let's say, some funny things to happen. In reality, we don't have a true triple bond in there. We've got some kind of overlap of orbitals, okay, that makes it appear and react for our purposes as a triple bond. But in reality, there's not really a triple bond there, okay? And if I haven't, I will link you guys a good resource that kind of talks about this. And it is kind of interesting to understand that, right? But for practically speaking, we've got a triple bond there, right? This is our benzyne as opposed to benzene intermediate, right? So there's that. Okay, what happens next? What happens next? I'll show you guys what the book does, and then I'll come back and make an argument about, something else real briefly, right? So now we've got, let's do this. So we've got red here, okay, and we've got black there, okay? So you see we've got these two carbons that are involved with that triple bond, right? So either one of those are equally reactive in this case, right? And so what will happen is the next incoming group can hit here or here, and that's what's going to be the difference in our mechanism, okay? So here's what the book shows. The book shows the base coming in, okay, and doing this. So it hits one of those. Could I have hit the black carbon? Absolutely, right? Doesn't really matter, and I'm going to continue this down here just for space, right? So we got this, this. Let's see, in green now, right? We brought in that. And over here, we've got that negative charge. This was my red carbon, and there's my black carbon, okay? Perfect. Not quite done yet. We're left with a negative charge. Got to deal with that. And so what happens then is our solvent, right, gets deprotonated, and that leaves us with our product. Green NH2, and then we have that green hydrogen coming from our solvent there. Fantastic, okay? And we could go back, and I would strongly suggest that you do, is, as practice, go in and see what happens with the black carbon there and the resonance structures, all that kind of stuff, okay? So that is the other mechanism that happens for nucleophilic aromatic substitution, okay? We either have this, what they call the elimination addition mechanism, aka making the benzyne, or we have the other substitution mechanism, which they call the SnAR mechanism, okay? So substitution nucleophilic aromatic ring, right? So either one, and page 832 is kind of the good summary of this, right? 832. Kind of gives you a little flow chart there, although in reality, right, we've only got 3 reactions, so it shouldn't be too hard to kind of pick those out there, right? So those are the 2 mechanisms that are at play with nucleophilic aromatic substitution. And that should give us plenty of tools to be able to modify an aromatic ring, bring an aromatic ring together with another compound, add functional groups and all this kind of stuff with it, right? So again, the big important thing to remember with these are we need withdrawing groups to add the OH in there, right, to do the SnAR mechanism, okay? And to do this reaction, the problem that we have with that is that we end up generating a mixture of products that are in there too, okay? I'm not saying that we can't be clever about things, and there's some good examples in the book that kind of talk about how to be clever, right? But this is definitely something that is maybe a little bit more limited in application than we might want it to be. So question then, okay? Here's a good question. So let's go back here, right? Let us say that we wanted to make this product, okay? Let's say that we wanted to make that product, and we started, and we're starting just from our good old buddy benzene, okay? Can you guys come up with, let's say, can you guys come up with 2 different ways of turning benzene into that product? Is it going to take more than 1 step? Absolutely. Okay, is it going to take 15 steps? I sure hope not, okay? So see if you guys can come up with a couple different ways to get to our product there. And think about and draw your mechanisms along the way and see what you guys can come up with, okay? So that's it. That's basically the gist of chapter 18. And that should be the end of the lectures that we have for the moment. I will continue to be posting some stuff for you guys along the way though, okay? So please reach out to me if you have any questions, and I will see you guys next time.